Okay, we are next going to start a new set of exercises. So the first one is this. Which of the following binary operations are closed? Okay, so we have 4 subdivisions here. The first one is subtraction of positive integers. Part B, division of non-zero integers. And then part C, function composition of polynomials with real coefficients. And part D, multiplication of 2 by 2 matrices with integer entries. Okay. The operation in part A, this is clearly not closed. It's not closed because if you subtract 2 from 1 and 2 both are positive integers, then the result is not a positive integer. So it's not closed. Like that, part B is also not closed, division of non-zero integers. Because if you say divide 1 by 2, then this is not an integer. 1 and 2 are non-zero integers, but their division in this fashion does not give us an integer. Part C, function composition of polynomials with real coefficients. If you take 2 polynomials, now here I am not going to write it is closed, that much I will write. But why is it closed? I won't show the general thing. What I will do is that I will take 2 polynomials, say fx equal to anything you can take, x cube minus 1 say, and say gx is equal to x square plus 2x. Now we can compose these two functions in two different ways. Both the compositions make sense. We can form the composition F composition G. Then you will first apply G on X, and on that you then will apply F. So if we first apply G and then apply F, then ultimately we will have this x square plus 2x whole cube minus 1. If you use binomial expansion, you will get what? So you see that you have ultimately you are having a polynomial. The other composition that can be formed is this G composition F of X. So here you will have x cube minus 1. First we are applying F, and on that we are applying G whole square plus 2 times x cube minus 1. Here also we can expand. We will get, doing so, we will get x to the power 6 minus 2x cube plus 1 plus 2x cube minus 2. So this gives us x to the power 6 minus 1. So we end up having a polynomial. From this example, you can imagine that if you have general polynomials here and you form such a composition, then what you are doing is that in place of x in the expression for one polynomial function, you are writing another function, and in doing so you are actually calculating powers of that polynomial, non-negative integral powers of that polynomial. That means you are multiplying polynomials, multiplying those powers by real numbers and then adding such terms, so that ultimately will give you a polynomial. So that's why this operation is closed. This is not closed, this is not closed, this is closed. The fourth one is also closed. And the reason is very simple. If you take 2 by 2 matrices with integer entries and multiply them, then the product will have these entries. Okay, I have to write a little carefully so that I have space, or let me write it here in a new line. AE plus BG, AF plus BH, CE plus DG, CF plus DH. Now here A, B, C, D, E, F, G, H, these are all integers, and in these entries you can see that the operations we are using are addition and multiplication of integers. So ultimately these entries are also integers. So that's why the result is again a 2 by 2 matrix with integer entries. So that's why this is closed. So This completes the first solution. The second one I think is also like this. Which of the following binary operations are okay? Now they are not talking about closure property but associativity, are associative. Multiplication mod n Part B, division of non-zero rationals. Then part C, function composition of polynomials with real coefficients, same like before. And part D, multiplication of 2 by 2, again that same thing, matrices with integer entries. Okay, so there was no actual need of rubbing that part off. The solution A, we know this multiplication, this operation is associative. This is known to us. This one, division of non-zero rationals, is not associative. Because if you consider this, say, okay, then that means what? If you are using the rules of division, the laws of division, then this becomes, or you can use the other form of writing these fractions. This is equal to 1 divided by 6. However, this is not equal to this thing, because this second one is something else. This is equal to 3 divided by 2, and 3 divided by 2 and 1 divided by 6 are different rational numbers. They are rational, no doubt, but the operation is not associative. Part C. It is associative because we know that in general function composition is associative. So in particular in this under the restriction that the functions being considered are polynomial functions, also the associativity will continue to be true. And just like that, multiplication of matrices is also an associative operation. So this one is also associative. Then exercise 3. Which of the following binary operations are now commutative? Part A. Subtraction of integers. Then part B. Division of non-zero real numbers. Then part C. Function composition of polynomials with real coefficients. And the last one obviously is matrix. Yes, multiplication of 2 by 2 matrices, but now with real entries. The first one is very easy. You can already see that it's not going to be commutative. Because subtraction of integers. 1 minus 2 is equal to minus 1, which is not equal to 1, that is 2 minus 1. So because of this, subtraction of integers is not commutative. B. Division of non-zero real numbers. Again, it's not commutative. this is not equal to 2 divided by 1. Function composition of polynomials with real coefficients. Unlike the associative property which is true for function composition in general is not commutative. In fact, we have already seen that when we consider those two examples, fx and gx. We can take two more. Consider the polynomial functions with real coefficients. Say fx equal to x plus 1, and we take simple ones so that the calculations of the compositions are not very complicated, and at the same time they serve our purpose. Now f composition g of x, so here first you apply g and then on that you apply x, so you get x square plus 1, and g composition f of x is x plus 1, first you apply f and then on that you apply g. So using the binomial theorem you get x square plus 2x plus 1. Note that f composition g as a function is not equal to g composition f, because when are two functions not equal, when of course their domains and ranges may be different, but that is not the case here. Here the fact that they are not equal will be shown by showing that they have different images for at some input. X square plus 2x plus 1, yes. So we can take f composition g of minus 1. This will be what? If you substitute minus 1 here, minus 1 square plus 1 gives you 2. Whereas if you substitute minus 1 here, you get plus 1 minus 2 plus 1. So that gives us 0. This is not equal to 0, and 0 is equal to g composition f of minus 1. So that's why function composition of polynomial functions with real coefficients is not, the operation is not commutative. In general also function composition is not commutative unless you restrict your functions to some very special sets, then it may become commutative. And finally, multiplication of 2 by 2 matrices with real entries is also not commutative. That means in this exercise none of the operations is commutative. D it's not commutative because let us take two I have taken two 2 by 2 matrices here, but you can take any, any arbitrary 2 by 2 matrices. Most likely they will not commute with each other. Minus 1, say 1, 1. If we calculate this product, what do we get? 2 plus 1, 3. Minus 1 plus 1, 0. 0 plus 1, 1. 0 plus 1, 1. Now if we change the order of these matrices, then we get 2 plus 0, 2. So in the very first row, first column entry itself, that they are different. 2 minus 1, 1. 1 plus 0, 1. 1 plus 1, 2. So that's why this operation is also not commutative. Okay. Then exercise 4. Which of the following sets are closed under the given operation? Part A, 0, 4, 8, 12. And the operation is addition mod 16. Then B, 0, 4, same set. Addition mod 15. Part C, 1, 4, 7, 13. The operation is multiplication mod 15. And part D, 1, 4, 5, 7. Multiplication mod 9. Okay, so you just have to perform the operations and see whether the results again belong to this set. If you add anything with 0, you get that thing back. So here, for example, 0 plus 0 is 0, 0 plus 4 is 4. So such results of such operations are clearly in the set in any order also if you perform them, that is either you perform 0 plus 4 or 4 plus 0, you are going to get 4, and 4 modulo 16 is 4, so you will get those things. So there is no point in considering the 0 as one summand. 4 plus 4 is 8, you have that here. 4 plus 8 is 12, 4 plus 12 is 16, 16 mod 16 is 0. Like that, if you form all the possible operations, I mean the operation addition modulo 16 among all the possible pairs of elements from this set, you will see that all such results will again belong to this set. So this set is actually closed. B. What about this one, modulo 50? This one is not closed because if you perform the operation with, if you add 8 with itself using this operation, then that is equal to 1. You have to understand this is not ordinary addition, it's addition modulo 16. If you want, you can use some other symbol here, but I'm just for the sake of showing, I am showing this fact that 8 plus 8 is equal to 1 under this operation, and 1 does not belong to the given set 0, 4, 8, 12. So this one is not closed. Then part C, 1, 4, 7, 13. This one is closed. This you can verify directly. Then part D, this set under multiplication mod 9. Okay, this again is not closed because if you perform this product, then the result is 2. 4 times 5 is actually equal to 20. 20 minus 2 is 18, which is divisible by 9. So that means 20 mod 9 is equal to 2, and this does not belong to the given set. So not closed. Always remember one thing, these are just some hints given to you. Some of these solutions, unless the exercise is very complicated or the solution needs many intricate steps, I am not supplying the full details. So never write a solution like this. Always write a solution as if you are presenting the solution to someone, or rather you are sending the solution to someone through, say, mail, so that if the person reads the solution, he or she will understand. It should be complete. Okay, so these are just some hints to show you what can be done. Then exercise 5. In each case, find the inverse of the element under the given operation. Okay. Find the inverse of the element. Under the given operation. 13 in Z20 or Z20, B 13 in U14, then C n minus 1 in UN, where it's given that n is greater than 2, and then D 3 minus 2i in C star, the group of non-zero complex numbers. Under multiplication. Okay. So Z20 or Z20 is the group of the integers from 0 to 19. I mean, it's been given in this text as integers. The elements have been given as integers. Truly speaking, they are not considered as integers, they are considered as congruence classes modulo this 20. This is the modulus of the congruence relation. However, in this book they have, I mean, you can consider them as integers and you can modify the operation addition modulo 20 to actually mean an operation between integers, such that, say, if you perform this operation a plus b, where a and b are integers, then the result of this operation is equal to the remainder when the ordinary integer a plus b is divided by 20. That way you can define, and that's what they have done here in this text. In Herstein's algebra, however, the elements in this group are considered to be congruence classes modulo 20. Same thing, they are isomorphic, but those things we will see later. Okay, so now, since 13 plus 7 is equal to 0 under this operation, okay, this is not ordinary addition, is equal to 7 plus 13 in Z20, the inverse of 13 in Z20 is 7. That is the inverse by definition of an inverse. Like that, we have to find the inverse of 13 in U14. U14, on the other hand, is the set of those positive integers that are less than 14 and relatively prime to 14. And the inverse here is this. Since 13 times 13 is equal to 1. The meaning of this equation is that if you calculate 13 square, ordinary 13 square, as a product of these two integers 13 and 13, you get 169. That if you divide by 14, the remainder is 1. Okay, so the remainder is 1, and we know that in U14 1 is the identity element. So the inverse of 13 in U14 is 13 itself. Then part C. In part C, a general group is given UN, where n is an integer greater than 2. And we have been asked to find the inverse of n minus 1. That is just like this one. Here we have 14, 13 in n minus 1. And like this one, here also the inverse will be n minus 1 itself. Since n minus 1 times n minus 1 is equal to 1. Okay, by the way, do you see why this is 1? If you actually calculate this product, what do you get? N square minus 2n plus 1. That n square minus 2n is equivalent to 0, because if you divide that part by n, then it's fully divisible, and so you are left with 1. And since it is given that n is greater than 2, so this 1 will be a remainder because it's less than the divisor n. So that's why this is equal to 1. In fact, this tells us also that 13 times 13 is equal to 1, because you can make, instead of actually calculating the product, you can think of it as 14 minus 1 times 14 minus 1, and you can argue like this to conclude that the remainder will be 1. Okay, so this in, or that I have to write in UN, and n is greater than, I need not write this part, because the fact that n is greater than 1 has made this calculation possible. In UN, the inverse of n minus 1 in UN is itself. And then in D we have the multiplicative group of non-zero complex numbers. Since the complex numbers form I should not say about fields at this stage. Okay, sorry about that. If you consider the non-zero complex numbers, they form a group under multiplication of complex numbers. In that group, this non-zero complex number will have an inverse, and that we have to find, which you know is simply the reciprocal of the complex number. In C star, the inverse of 3 minus 2i is just simply this, but let's express this in standard form. You multiply and divide by the complex conjugate of the denominator. So that gives us 3 plus 2i divided by 3 square plus 2 square. So 9 plus 4 is 13. So 3 divided by 13 plus 2 divided by 13 times I. This is the inverse. Okay, so this was exercise 5. Next exercise 6. In each case, perform the indicated operation. So these exercises, most of them I see at this stage at least, are sort of practice exercises. They are not that involved, but the involved exercises which need some original ideas and thinking on our part, they are coming. Part A, in C star, calculate this product 7 plus 5i times minus 3 plus 2i. Okay. Part B, in GL2 comma Z13. So this is the okay, we will discuss about these groups later on. Let us first take the exercise down. 7415. In GL2 comma R. Six, 3, 8, 2. For this matrix, we have to find the inverse. And then in part D, same matrix, but the group is different. Okay, the first one is very easy. We have to just multiply these two complex numbers. Seven times minus 3 is minus 21 minus 10 plus 7 times 2 is 14i and minus 15i. So this becomes minus 31 minus I. So this is the product. Part B. So this is the general linear group of 2 by 2 matrices where the entries are coming from this set Z13, which itself is the group of integers starting from 0 all the way up to 12, and the operation is addition modulo 13. And not just any 2 by 2 matrices, those 2 by 2 matrices which are non-singular, that is, whose determinants are not equal to 0. Here we have to calculate the determinant of this matrix. So the formula for the determinant we already know, but after we get that after we apply that formula, then the calculation will be done in Z13. 7, 4, 1, 5. So this is equal to 7 times 5 minus 4 times 1. 31 minus 26. Okay, 5. So this is equal to 5, because if you divide 31 by 13, then the remainder is 5. So that is the answer. Part C. Just like that, this is the general linear group of 2 by 2 non-singular matrices, but here the entries are ordinary real numbers. Okay, but we have to find here the inverse. To find the inverse, we of course should also know the determinant. Or let us calculate we can calculate the determinant here itself. 6 times 2 is 12, minus 3 times 8 is 24. So the determinant is minus 12. And the inverse, the formula for the inverse is this: 2 divided by minus 12, minus 3 by minus 12, minus 8 by minus 12, and 6 by minus 12. So the formula we are using here is this. Say you have a 2 by 2 matrix like this, where the entries may be real numbers or may come from a finite number system like this, it does not matter. The formula for the inverse is this: you interchange the positions of A and D, the leading diagonal entries, for them you interchange the positions. D, here you have A. You don't interchange the positions of B and C, that is, you keep them in their positions, but supply a minus sign with them. Minus B minus C, and you divide all the entries by the determinant, that is AD. If I say denote the determinant AD minus BC by delta, then D by delta minus C by delta minus B by delta and A by delta. Okay, this is only the formula for the inverse of a 2 by 2 matrix. For a 3 by 3 matrix, it is totally different. That's what we have done here. And now we can simplify this. So this becomes minus 1 over 6, 1 over 4, so both of them are divisible by 4, so 2 over 3 and minus 1 over 2. So this is the inverse. You can multiply the original matrix without the inverse with this one and see whether you are getting the 2 by 2 identity matrix or not. You will get that. Okay, so this is the inverse, and lastly we have D. We still will have this, but you have to make sense of these entries differently. Modulo 13. Now modulo 13 minus 12 is equal to 1, because if you take the difference of minus 12 and 1, then that difference is divisible by 13. So here actually you don't have to divide by anything, because you are dividing by 1, because minus 12 is equal to 1 modulo 13. So here the thing is 2 minus 3 minus 8 6. So modulo 13 minus 3 is 10 and minus 8 is 5. So this is the inverse. And the solution ends here. Then exercise 7. Give 2 reasons why the set of odd integers under OK. Two reasons why the set of odd integers under addition is not a group. The sum of two odd integers is not odd. In fact, it is even. So that's why under addition the set of odd integers is not closed. So that is one reason. Another reason is this. There is no identity element. If A and B are odd integers, such that A plus B is equal to A, which is equal to B plus A, so that B plays the role of an identity, then B is equal to 0. But B is an odd integer, so these equations demand that B must be equal to 0. So that's why there is no identity element in the set of odd integers with respect to the operation of addition, which is not possible. Okay, so this is another reason for this system to not be a group. Next, exercise 8. Referring to example 13. Verify the assertion that subtraction is not associative. So in example 13, I think the set we have is the set of integers, or maybe the set of positive integers. I don't remember exactly, but to be on the safe side, let's consider positive integers, and using them, let us show that subtraction is not associative. It's very easy to find a counterexample. I'm just going to write the the relation, which is not an equation, it's a non-equation. If you form this expression 1 minus 1 minus 2, then what do you get? 1 minus 2 is minus 1, minus of minus 1 is plus 1, 1 plus 1 is 2. However, on the other hand, if you form this expression 1 minus 1 minus 2, then you get minus 2, and these two things are not equal. So that's why subtraction is not associative. This is minus 2. Exercise 9. Show that 1, 2, 3 is not a group. This set under multiplication mod 4 is not a group. But this set under multiplication mod 5 is a group. This is not a group under multiplication mod 4 because 2 times 2 is equal to 4 actually, but mod 4 is equal to 0. I need ink, more ink. So this is equal to 0, and 0 does not belong to the given set. So the operation is not even closed. So how can it form a group? I mean, how can this set be a group under that operation? Verify, or should I do this for you? Now I leave it to you. Verify that this is a group under multiplication mod 5. Here you have to actually form the Cayley table, but you can also solve the exercise by not forming the Cayley table. All you have to do is you have to perform all the multiplications, 1 times 1, 1 times 2, 2 times 1, those things you perform, and you see that modulo 5, the results that you get, they are again in this set. That will prove that this set is closed under multiplication mod 5. Then multiplication mod 5 is an operation which we already know is associative, so that part is also gone. And then you will see that 1 acts as an identity element for that operation. And then finally you have to find the inverse to every element. The inverse of 1 will turn out to be equal to 1. The inverse of 2 will be actually equal to 3, because if you form the product 2 times 3, you get 6, which mod 5 is equal to 1, which is the identity. So 2 and 3 are inverses of each other, and you will see that 4 is the inverse of itself, because 4 square is 16. 16 is equal to 1 mod 5, because 16 is 5 times 3 plus 1. So you get all the inverses, and hence it's a group. You just have to write these things systematically. Then exercise 10. Let's solve a few more. Show that the group GL2R, general linear group, of example 9 is non-abelian. By exhibiting a pair A and B such that AB is not equal to BA. We have already done this once, and we are going to refer to that. C the solution to part D of exercise 3. That is, you have to come up with two 2 by 2 matrices with real entries which do not commute, A and B, such that AB and BA are different matrices. We have already done it in exercise 3, so you can use those matrices. Exercise 11. Find the inverse of the element 2, 6, 3, 5. Set 11. Okay. Ideally, you should write like this. The inverse of this matrix in this group is, because otherwise this looks just like inverse of this ordinary matrix with real entries. That's not the case here, because the group from which the entries are coming is not R, is not the additive group of real numbers. In fact, we are not considering these sets from which the entries are coming as a single group, because to perform matrix multiplication and also to find the inverse of a matrix for which inverse exists, you have to consider both the operations, addition and multiplication. These systems, that is the system of real numbers or this finite systems, they are examples of fields. We will see fields at one stage in this text. So so what is the determinant here? The determinant is same, the formula is same. 2 times 5 is 10 minus 3 times 6 is 18. So this is equal to minus 8, and excuse me, modulo 11 minus 8 is equivalent to 3. Now we should divide, here we have to divide by the determinant to find the inverse. We have to divide by 3. Dividing by 3 in Z11 means multiplying by the inverse of 3. Now what is the inverse of 3? You can see that 3 times 4 is 12, which is equal to 1 in Z11. So the inverse of 3 is 4. So we have to multiply by 4 the necessary, the entries in the formula, and they will be 5 times 4. You interchange these two things, then 2 times 4. You don't interchange these but change their sign, and minus 3 times 4. And again, after performing these multiplications, we have to reduce all the entries modulo 11. So this is 20, that means 9. This is minus 24, from which minus 22 will vanish. We will be left with minus 2. So that is again equal to 9. Then this one is minus 12. From minus 12, minus 11 will vanish. We will have minus 1. 11 minus 1 is 10. And this one is simply 8. So this is the inverse. 9, 9, 10, 8. Let's do one more. Exercise 12. Give an example of group elements A and B. with the property that A inverse BA is not equal to B. Note that this property is equivalent to having BA and AB as different, because these are supposed to be elements in a group. So if you multiply both sides of this equation from the left by A, on the left hand side you will have BA, on the right hand side you will have AB. Now why would those two products be not equal? Because if they are equal, then by the cancellation laws, that is, you can cancel A from both sides to have the equation A inverse BA is equal to B. But it's given that that is not the case, so these two products will also be different. So that means essentially you have to find two group elements which do not commute, and which again we have already seen matrices. So you can directly write the solution like this. In our familiar group, general linear group of 2 by 2 matrices with real entries, take the elements. A is the matrix, say 1 0 2 1, and B is the matrix -1 1 1 1. But there is one thing that may cause you to make a mistake. You see, the group we are considering is the general linear group. So the matrices you consider not only should not commute, but they also should be invertible. Their determinants should not be equal to 0. In this case, you see the determinant is 1. Here the determinant is -1 -1 -2. So they are actually elements in this group, and they do not commute, which can be verified, which has to be verified if someone wants to write a complete solution. So I end the video here itself. We will see more of these exercises in the coming parts. If you have any doubt or any queries regarding these things, you can write in the comment section below. So with that, I sign off for tonight. This is me, Lucifer, from A Mathematical Room. Have a nice night.